Hello everyone. So today I'm going to talk about how we can use the Euclidean algorithm to find modular inverses. So first of all, we actually talked about the Euclidean algorithm before back in Unit 3. In Unit 3.1, in the notes, I talked about how we can use the Euclidean algorithm to find the greatest common divisor. So you should read the 3.1 notes if you haven't yet done that. And I'm just going to briefly review that. So to find the greatest common divisor using the Euclidean algorithm, first of all, we write the two numbers next to each other. We write the big number first. So let's say we wanted to find the greatest common divisor between 63 and 42. So we write the numbers together, and then what we're going to do is that we're going to take the remainder when dividing the big number by a small number. So the remainder when dividing 63 by 42 is 19 and 21. And then we look at these two numbers, 42 and 21. So if we divide them, then the remainder is 0. And then when we get a remainder of 0, then the greatest common divisor is the number before the 0. So in this case, the greatest common divisor of 63 and 42 is 21. So let's do another example. Let's say that we wanted to find the greatest common divisor of say 39 and let's do 53. Actually 54. I'm gonna write 54 first. So again, we're gonna take the remainder when dividing 54 by 39, and in this case that should be 15. And then we're going to take the remainder dividing 39 by 15. So twice of 15 is 30, so the remainder is 9. And then we take the remainder of dividing 15 by 9, which is just 6. And then the remainder of dividing 9 by 6, which is 3. And then we get the 6 divided by 3, the remainder is 0. So the greatest common divisor is 3. Now, so that's how you find the greatest common divisor. So that's the Euclidean algorithm, basic Euclidean algorithm. Now, to find the modular inverse, we use what's called the extended Euclidean algorithm. So, let's say we have a modulus 41, and then let's say that we wanted to find the modular inverse of 5. So we write the modulus first and then the number. Now we're gonna do the Euclidean algorithm here, but we're gonna keep track of a couple extra numbers. So below we also write 0 and 1. Now like before, we're going to take the remainder of 41 divided by 5, which is 1. But we also want to keep the quotient. So 41 divided by 5, that's 5 times 8 is 40, so the quotient is 8. Okay, quotient is 8, remainder is 1. Now, we take 8, we multiply it by the number underneath it. So 8 times 1, that's 1, and then we subtract it from the number before it. So we do 0 minus 8 times 1, which is negative 8, of course. So we put negative 8 here. And then we repeat this. So 5 divided by 1, the quotient is 5, and the remainder is 0. Now, once we get a 0 here, first of all, we want to look at the number before the 0, which is the greatest common divisor. And if this greatest common divisor is not 1, then there is no modular inverse. because there's only a modular inverse if the modulus and the number are relatively prime or co-prime. So, and if they're co-prime, then the greatest common divisor is 1. So there's only an inverse if the greatest common divisor, the number before the 0 here, is 1. Now, it's 1 here, so we know that there is an inverse, and the inverse is the number directly below on the bottom here. So, and here it's negative, but we can fix this by just adding the modulus. So if it's negative, then we just add the modulus, negative 8 plus 41, because when you add the modulus, that in modular arithmetic, that doesn't really change the number. So negative 8 plus 41 equals 33. So this right here is the inverse. It's the inverse of 5 mod 41. So to verify this, we can do 5 times 33 mod 41. So 5 times 33 is 165, and then 165, if you take the remainder here, that's 4, that's 164, remainder is 1, so 5 times 33 is congruent to 1 mod 41, which means that 33 is the inverse of 5, so the inverse of 5 is 33 mod so the inverse of 5 is 33 mod 41. So let's do another example. Let's say we had modulus is 97, and then let's say we wanted to find the inverse of 42. So again, we do 97, 42, and we do the division here. So 97 divided by 42, quotient is 2, so 2 times 42, that's 84, and then the remainder is 13. And then we have 0 and 1 here. So we do 0 minus 2 times 1, so that's negative 2. And then we do 42 divided by 13, so the quotient is 3. 3 times 13 is 39, so the remainder is also 3. And then we do 1 minus 3 times negative 2. 3 times negative 2 is negative 6. 1 minus negative 6 is 1 plus 6, which is 7. And then we're going to take the, we're going to divide these two numbers. 13 divided by 3, the quotient is 4, and the remainder is 1. And then we're going to take 4 multiplied by 7, that's 28, negative 2 minus 28, so negative 30. And then again, take the quotient, 3, remainder is 0. And we got 0, and the number before it is 1, which means that we do have an inverse, and the inverse is negative 30. So again, it's negative, so negative 30. We're just going to add the modulus plus 97. Negative 30 plus 97, that's 67. So the inverse of 42 is 67 mod 97. Now in both of these cases here, the number that we got was negative. If it's positive, then you don't have to do anything that's the inverse. If it's negative, you add the modulus to make it positive. So yeah, that's how you find the modular inverse using the extended Euclidean algorithm. You just do the extended Euclidean algorithm here, keep track of the quotients, and then on the bottom here, you take the number before, subtracted by the number after it, multiplied by the quotient. So 0 minus 1 times 2, 1 minus negative 2 times 3, negative 2 minus 7 times 4, and so on. There you go.